So a sequence is a function from the whole numbers to the real numbers. Can anybody tell me what the whole numbers are? Correct. As you see down here, does it include negatives? It does not. Most of the time when we say whole numbers, we would consider like -5 a whole number, right? Technically, those are not whole numbers. Integers is the word we use if we're talking about positives and negatives of all of the whole numbers. So whole numbers does not include negative numbers. So the only numbers we can plug into this equation are 0, 1, 2, 3, 4, 5, 6, and so on. But we get any real number. Real numbers includes almost all numbers. Definitely all the numbers that we think about a lot. It includes, obviously, all the whole numbers. It includes all the negatives and the integers. It includes rational numbers. Rational numbers, how can they, what makes something a rational number? It can be written as a fraction. Very good. So it would be anything that can be written as a fraction. It includes irrational numbers. What are irrational numbers? Or like an example of an irrational number. Pi is a great example because it is a non-repeating decimal that goes on forever and ever. Another example would be something like the square root of 2. The square root of 2, right? And we can't take the square root of 2, not without a calculator. And when we do take the square root of 2 with a calculator, it gives us this big long decimal. And that decimal actually keeps on going forever. So irrational numbers are also real numbers. All right, can anybody tell me something that is not a real number? I is not a real number. So you will not get out of this anything that has an I with it, right? But pretty much any other number is fair game that you can get out. Okay? Now, if we graph this, because we're only plugging in whole numbers, we're only plugging in 0, 1, 2, 3, 4, our graph is only going to be points. Okay? It will not be, those points will not be connected, right? It is going to just look like let's say we had a quadratic, it would just look like this. Those points would not be connected for that. So these are very similar to functions, but they're a little bit different because they're not connected. You're only plugging in whole numbers to them. So do the next slide for me. There. Okay. You have not seen the phrases arithmetic and geometric sequences yet, but I bet that you can answer these questions. And if you need your calculator on some of these, some of them are a little trickier to just like figure out easily in your head. That's okay. You guys will please put your phones like away in your book bag so that not on your desk. Okay, so questions like this, questions like number 2, you would have seen since 3rd grade, right? As soon as you learned how to multiply, you may have seen something like number 2 in 3rd grade. You probably wouldn't see example 1 in like 1st or 2nd grade because of those negatives, but if I had done that same pattern without negative numbers, if I had done 1, 4, and then a couple more, you might have seen it in like 1st grade, right? I'm pretty sure Henry has some problems that look like this in 1st grade. These are geometric and arithmetic sequences. It's just patterns. So what would be the next numbers for number 1? Lucas, what would you get?
7.
Good, and, oh, well, that's not right. All right, then what would you get? Good, and 13, right? Our pattern is that we're just adding 3 each time, right? Okay. Let's see, Ethan, how about number 2? We're multiplying by 2, so what would the next one be? Good. Good. 96, I think. Yeah. Okay, so just multiplying by 2 each time, right? Both of those we would have seen really early on. 3 and 4, a little bit later, because we do have some decimals and stuff there, but still, everything right here could pretty much be done in elementary school. I don't know if they multiply with negatives much in elementary school, but if I'd left the negatives out, definitely all of it could have been done in elementary school, right? For the next one, Solana, what's happening on that one?
Adding decimal 65.
Okay. What would you get for your next numbers?
10.2, and then 10.85, and then 11.5.
Okay, great. Okay. Last one's just a little bit trickier. What's happening on the last one there, Granger? Very good. What are the next numbers?
16,
Perfect. And if you ever see that alternating positive, negative, positive, negative, positive, negative, you're probably multiplying by a negative number, and that's what's happening each time there. So if you see the alternate, like here we weren't alternating between positive and negative, right? But here, positive, negative, that's got to be a multiplying most of the time, or a more complicated one that we can't do. There is like a neither option. We actually don't have to go into any in this class. We just need to identify it as neither for these. So this is stuff that, although you haven't looked at it formally, you know how to do a lot of it already. So let's look at it formally and look at the notation that you're going to see with this. So for the notation that you are going to see a lot of times, instead of using things like y equals 2x plus 7, we're going to have this notation where we will have like an A with a subscript behind it. Or we might have a G with a subscript. The notes for these I used Mr. Passwater's notes to kind of help me make my own notes. I didn't like the way he did his. But he used a G whenever it was a geometric sequence. But this could really, that A could be any letter. It could be F, it could be T, just like F of X, G of X, that sort of thing. But A with a subscript of N means that is the nth term. So if you have A sub 0, it is the 0 term. We'll call that the initial value. N is the whole number that is entered into the sequence. So if you're plugging in 7, that's your N for that. So like if I wanted the, well, let's just do this next problem. So for the sequence, A sub N equals 3N minus 7, we're supposed to find A sub 4. Okay? That is just telling me that I'm looking for the result when I plug 4 into the equation for N. Right? This is because if we got A sub N and I'm looking for A sub 4, that tells me that N must equal 4 for that, right? So all we're doing for this is doing 3 times 4 minus 5, which is going to be 12 minus 5, which will give us 7. That'll be our answer. This is very similar to this. If I've got f of x and it is 3x minus 5, and they ask me for f of 4, I would do pretty much the same thing, right? This is function notation. In function notation, I can plug any number in. I can plug in 1.7. I can plug in the square root of 24. I can plug in whatever number I want in function notation. Whenever it's sequence notation, you can only plug the whole numbers in. But we're going to see they behave a lot the same for that. So if I'm looking at the second question here, what am I doing to that equation? I'll be squaring because I'm plugging in 2 for that n, right? So I'll have a sub 2 would be 2 times 3 squared. Let's do this without the calculator. What have I got to do first? Yeah, I got to do the square because there's nothing like to do inside of those parentheses. So exponents would come next. So that would be 2 times 9, and that would be 18. A lot of people get 36 for that answer. Because what would you do wrong if you got 36? Yeah, 6 and then square it, right? You got to do exponents first before you multiply for that. Some of this stuff, the easier stuff will be on the calculator inactive. Some of the stuff like you saw earlier with those decimals, I'll probably put that on calculator active just because you could do it by hand. It's just going to take a long time. All right. Again, similar to the idea of having like f of x equals 2 times 3 to the x power, and you're plugging in 2, like finding f of 2 there. Now, best I can tell, let's see, this is the next one. Okay, best I can tell, we don't have to do this. But I can just not teach this without showing you this right here. Because whenever I taught pre-calculus before, what I'm getting ready to show you was the focus of this section. It's what we did primarily. But when I look at the AP stuff, the questions and stuff they put out there, they do not have a single question that I have seen that has this a sub n minus 1. So I just can't go by this without showing this to you. But I'm not going to ask it on the test, and it's not going to be, I don't think it's going to be anything you're going to see. There's a tiny chance it might show up on the like ACT, so it won't hurt for us to go over it. I'm not sure. I can't remember for sure there. But normally, whenever I teach this, we really focus on recursive formulas. And recursive formulas are going to work with a sequence, but rather than having just an n in the equation, which is what we'll call an explicit formula, where you just plug the number in and it spits the answer out, we'll have something like a sub n minus 1 for that. So I just want to go over briefly what you would do for this. Okay. So we've got the sequence a sub n equals 2 times a sub n minus 1, and they tell us that a sub 0 equals 5, and they ask us to find a sub 3. So if we think about what we just did, if I'm finding a sub 3, that means I'm plugging in 3 for a, for n. So that means I would have 2 a sub 3 minus 1, which is a sub 3 would equal 2 times a sub 2. I don't know a sub 2, right? I don't have anything I can plug into that. But essentially, this just means you're multiplying, like if I'm trying to find a sub 3, I'm multiplying the term that came before a sub 3 by 2, right? So this a sub n by minus 1 is the prior term, right? So to find a sub 3, I would just multiply a sub 2 by 2. But I don't have a sub 2. So then I'd have to find a sub 2. And if I did that, I need a sub 1, right? And to get that, I need a sub 0, which I do actually have. So what you can do for this, the formula is just telling you to take whatever term you have, which we have a sub 0 equals 5, to get the next term, right? To get a sub 1, I would do 2 times a sub 0, right? Because if I'm doing a sub 1, it would be 2 times a sub 1 minus 1, which would be 2 times a sub 0. So 2 times 5 would give me 10. And then a sub 2 would be, a sub 2 would be 2 times a sub 2 minus 1, which is 2 times a sub 1. We're just multiplying the term by the prior term. So that'd be 2 times 10, which would give me 20. And then what are we going to get for a sub 3? It's going to be 40. Right? So this rule is just telling me that my pattern is to take the prior term and multiply it by 2. So I'm just, 5 times 2 is 10, times 2 is 20, times 2 is 40 here. And so this is what we call a recursively defined function. Instead of just having an n, it's got like the term before that a sub n minus 1 is your prior term. For that. So 40 would be our answer there. Now, if I look at example 8, I'm asked for a sub 4, but they give me a sub 0. All right, so I've got to start from a sub 0, which is negative 2. And I'm going to have to find every term leading up to that. Because this is defined with prior terms. So if I'm trying to find a sub 1, my rule is telling me to take the prior term and subtract 4, right? So I would take a sub 0 and subtract 4. What will I get right there? Prior term was negative 2. I'm subtracting 4 from it, just negative 6, right? And then a sub 2 would be prior term, which is negative 6, minus 4. I get negative 10. A sub 3 would be the prior term, negative 10. Subtract 4, get negative 14. And then finally, my a sub 4 would be negative 18 for that. Now, if that's really confusing you, I don't think we have to do this. Now, this was like, I have a hard time even stopping here because we used to do so much with it in the prior calculus stuff. But best I can tell, we don't have to. So you've seen a touch of it if you run into it later. All right. So let's talk about some arithmetic sequences. Okay, arithmetic sequences are formed by adding a constant value to each successive term. That constant value, that number that you're adding each time, is called the common difference. Now, if I have a function and I look at the table, like I've got n, let's do n and a sub n, and I've got 0, 1, 2, 3, and I've got, let's say we got 4, 7, 10, 13, right? What am I adding each time? I'm adding 3, right? Adding 3, adding 3, adding 3. If I graph that, what's it going to look like? If I'm just adding 3 each time, it's going to be constantly going up, and I think I may have heard, it's going to look like a line. It'll just be points because we won't connect them, but those points are going to be in a line, right? This is a constant rate of change, right? So we've been talking about functions, we've been talking about rates of change. Arithmetic sequences have a constant rate of change. They're going to behave like linear functions, except they're not continuous. Rather than being a line, it's going to be a bunch of points that are in a line, right? But they're going to behave like linear functions. Arithmetic sequences have a constant rate of change. Okay, it's important here. Hello? She did not. You're welcome. Bye. Okay, so it's important to know this is called the common difference here. That is really common difference. If we're thinking like linear functions, it's like your slope of your graph. So it's going to be like that slope. And they're going to ask us for that fairly often. You also might want to put over here that usually they are going to denote common difference with the letter D. That's the letter they're going to usually use for that. Okay, so if we look at our next problem, one of the things we really focus on is multiple representations. What does this look like in a table? What does it look like on a graph? How do those relate to each other? So if I make a table for this, if I am looking at my n's and my a sub n, so my n is on this axis right here, it's on the x-axis, a sub n is on the y-axis. It's just like it is whenever you're using a function. The only difference is we can't plug in 1.5, right? We can only plug in 1 and 2 and 3 and 4. So if I plug in 0, I got 1/2 times 0 minus 3. I'll get negative 3. If I plug in 1, I'll get 1/2 minus 3, which is going to give me negative 2.5, right? If I plug in 2, I'll get 1/2 times 2 minus 3. That's just going to be 1 minus 3. That's going to be negative 2. What do you see happening here? What's happening each time?
25.
We're going down by 0.5. So, like, the next one's going to, or actually up by 0.5. 1.5, negative 1, negative 0.5 there. And so we are going to take these points and we're going to graph them over here. So I've got negative 0, negative 3, 1, negative 2.5, 2, negative 2, 3, negative 1.5, 4, negative 1, and 5, negative 0.5. Oh, what was I about to do? My habit just kicked in there. I was about to draw a line through that, and I cannot, right? This is a sequence, so let me back that up a second. These points are our graph. I want to draw a line so desperately there, but sequences can only have the whole numbers plugged in, so we're not drawing a line. We just have these points. There's a lot of things in life that would be sequences. We might treat them like functions, but like they would be sequences because you can only plug in a whole number, right? Like, for example, if you are going to go buy, you know, bracelets or something, right? And you want a bunch, if you're like Hunter sometimes, and you want a bunch of bracelets on your arm. Sometimes he's got several. A lot of times, I think he's gotten them from girls that give them to him. But, yeah, he's got, anyway, if you want lots of bracelets, you can go buy all these bracelets. You can only buy a single bracelet, right? The input value is always a whole number. The output can be any number depending on the price, but the input's only a whole number, right? So there's a lot of things in life. Sometimes we just treat them like functions anyway. There's a lot of things in life that do have to be sequences because you can only put whole numbers into them. So it's kind of interesting to look at. But you'll notice here, what is the, like if we think of this as a line, if we think of this as y equals 1/2 x minus 3, if we think of it as line, what's the y-intercept of that line? It'll be down 3, which is where I intersect the y-axis here. What's the slope of that line? 1/2, and that is what I'm doing here, like going up 1 over 2, up 1 over 2, right? So that slope and y-intercept of the equation, the function, corresponds to the slope and the y-intercept of these arithmetic sequences that we're seeing here. Notice that slope is that amount that's being added to each term each time here. So let's continue here. All right, so for example 10, what is the common difference for the sequence above? So I put this above. I did this above instead of below because the AP likes to format things that way better. Yes? I think that looks probably right. If we're not sure, how can we tell for sure? Yeah, if you just take a term and subtract the one before it, so let me open up my calculator here. Oh, that's the wrong thing. We're done with that. Actually, might need a second period. Leave that open. Or third period. Let me go. I want this to go over here. Let's make this bigger here. So if I just, if I take a term and I subtract the one before it, so negative 3.1 minus negative 5.5. I just subtract the two terms, I'll get the difference every time. Take a term, subtract the one before it. So yeah, you're just adding 2.4 for that. So that is correct. And you can sort of check. So the common difference, we'll call it D here, is 2.4. Okay, so 11 doesn't ask us for common difference. 11 asks us to write the sequence, write the equation for the sequence shown above. So we still need our common difference for this. What is the common difference for this? It's just plus 2, right? We can do that one without our calculator. So that common difference is 2. Remember, that's like your slope, right? So when we're writing this equation, we're going to have a sub n equals, and we're using a sub n instead of like our y or f of x. And then our slope is 2, so we're going to have 2 times n. What would the y-intercept be for this? It's going to be 6. It's just the first number that we get, because we're only plugging in whole numbers, right? So the first number that we plug in is going to be 0 for that. So if we plug in 0, we would get 6. That'll be our first in the list. So that would be our y-intercept. Now, down here at the bottom, for this, oops, let me go back. On presentation mode, I can't do it from here. Let me get out of presentation mode for this. Down here at the bottom, you have a block. So this is a shortcut for you. Just going to move it away. Arithmetic sequence can always be written as a sub n equals a sub 0 plus d times n. Okay, copy that down and then I'll explain what that means. A sub 0 is the term that you get when you plug in 0. And 0 is the first number you can plug in for a sequence, right? We can't plug in negatives for a sequence. So this is just your initial value. D right here is the common difference. So in an arithmetic sequence, your initial value is like your y-intercept, and your common difference is like your slope. All right, so it'll always be multiplied by the variable, which is n in this case. Okay, questions so far? All right, we're going to go back to presentation mode here, and get rid of this. Okay, try 12 on your own. Check with your label that you got, see if they got the same number as you. Seeing some different numbers as I walk around for sure. A lot of different numbers. I've actually done this one to see what we get. Let's see. Alright. Okay, I'm seeing I think 37, 40, I'm seeing 35, I think I maybe saw 27. I saw a lot of different numbers as I walked around. So the Alright, so the like brute force method to do this, they told you third term, that would be a sub 3. They told you it is 9. Right? And they told you the fourth term is 13. Alright, how much did that go up by? 4. Right? So just like brute force method, a to the 5th is going to be 17. Or not a to the 5th, a sub 5. A sub 6 would be 21. A to the 7th is going to be 25. A to the 8th, or not, I keep saying to the, that's incorrect. A sub 8 is going to be 29. A sub 9 is going to be 33. A sub 10 is 37. If you are one of the 37 people, you are correct. Good job. Now, if I have to do this, you can imagine that this would be kind of tedious if you are trying to do this for like the 20th term or the 100th term, right? That is going to, it's really, honestly, if they give you this question on the ACT or the AP exam, I would do it this way. This is how I would do it. I would just, it's not that hard. I'd write it down so I make sure I don't like hit my calculator button one too many times. This is the way I would do it if I was given this problem. But change that 10th to 20th or, you know, something big, then this becomes difficult to do because the likelihood that you go that far without making a mistake starts to go down. So let's think about other ways we could have done this, right? If I had an equation, that would be really helpful, right? Because if I had an equation, then I could just plug in 10. But I don't have an equation. I do know the common difference is 4, right? So I know a sub n is going to equal 4n. And then I don't know a sub 0. I could kind of do what I've done right here and go backwards and find a sub 0. A sub 2, what would it be? 5. A sub 1 would be 1, and a sub 0 would be -3, right? So I'd have like 4n minus 3. Or a lot of times, for whatever reason, they like to write these with the n at the end, like -3 plus 4n. I think because you're starting at -3 and you're adding 4 each time. That's the reason they write it that way, but either one is okay. So if I have this formula, then I can just do a sub 10 equals -3 plus 4 times 10. And then that will be -3 plus 40, which is 37. So sometimes it might be better to write yourself a formula for it. In this one, I probably wouldn't. Now, sometimes you also might have a hard time going backwards because maybe they give you the 10th term and they're asking you for the 90th term. And going backwards is going to be really difficult. So if they give you one that it's hard to go backwards for, here is a formula, and I'm going to have to exit presentation mode here. Get rid of this. And let me move this right here for this formula. I'll let you copy that down and we'll talk about what that means and look at how we would use it on this problem. Okay. So notice we've got a new number this time, or a new variable. We've got a k here. So k would be, so it's easiest if they tell us the initial term, if they tell us a sub 0. Then we can just basically write a sub 0 is your y-intercept, common difference is your slope. Basically just write a linear equation is what you're doing for it. But if they don't give you a sub 0, and they give you a different term, like the k right here. So in this case, they gave us, we could use either one, a sub 3 or a sub 4, right? We could say that it equals a sub whatever we have here, plus the common difference times n minus that value. So like, let me give you an example of how that would look up here. If I wanted to do that here, I know a sub 3 is 9. So if I wanted to write an equation for this, I could say a sub n equals a sub 3 plus my common difference, which was 4, times n minus 3, which the a sub 3 was 9, right? So I got 4 times n minus 3. So that could be my equation. And if I want to know a sub 10, then I would just plug in 10. So I'd get 9 plus 4 times 10 minus 3. So 9 plus 4 times 7. Now think about what you're doing here. You started at 9. You added 4 7 times. Because 4, that could be written as 4 times 7 is just plus 4 plus 4 plus 4 7 times, right? So that's what you did whenever you just made a list out and did it the long way. So this works out, and then of course that gives you 9 plus 28, which is again 37 for that. So lots of different ways to approach the same problem for this. Okay, questions? All right, let's talk about geometric sequences. Geometric sequences are formed by multiplying. Oh, and I didn't talk about this on arithmetic. I said arithmetic's always adding. Sometimes it looked like we were subtracting, right? But why can I say that you're just always adding? Yes, because they're inverses. So, like if I want to subtract, I really could just add a negative, right? That common difference ends up being negative for that. So when I say that you're always adding, I can say that, and then if I need to subtract, I just add a negative number, right? I'm going to do the same thing with geometric sequences. Sometimes they don't look like they're multiplying. What do you think they might look like sometimes? Huh? Sometimes they look like they're dividing, right? But what is the same, like if I am taking x and I'm dividing it by 2, how could I make that multiplication instead? That's an option. No, divided by decimal is gonna make it bigger. Okay, dividing by 2 is the same as multiplying by 1/2, right? So you're taking half of something. So in this case, if we see a sequence that looks like you're dividing instead of multiplying, what's happening is that you're actually multiplying by the fraction, or it might be a decimal that you're multiplying by. So like if I want to divide something by 2, I could just multiply it by 1/2 or 0.5. It's going to give me the same value. So we're going to work only with multiplying. If we need to divide, we're just going to multiply by the fraction for it. So the constant value that is being multiplied by every time is called the common ratio. Now, we haven't talked about these functions in this class yet. But if I have a function where maybe I start and my original value is 2, and I am multiplying by 3. So 2 times 3 is 6, and then 6 times 3 is 18, and 18 times 3 is 64, I think. Double check me on that. My mental math. There. So, 54? 54. Oops. Let's do 54 there. Okay. All right. So, if I'm looking at this, what type of function do you think that might be? Definitely not linear, right? We're not increasing by the same amount each time. This goes up by 4, and then it goes up by 12, and then it goes up by a lot more than 12, right? Does anybody know what that would be? Sometimes quadratics or cubics will look like this, but we've already talked about those in this class. It would not be it. It's exponential. All right, this is exponential growth. One thing I did notice on one of our last tests is that some of you used the phrase growing exponentially, like to talk about something getting bigger fast, which it does kind of look like that on a quadratic or a cubic. It gets bigger fast, but it's technically not exponential. For it to be exponential, then you are going to have an exponent in a variable in the exponent for that. But geometric sequences are going to behave like exponential functions. Except, again, they're not continuous. So if you graph them, it's not a line, it is dots, right? Geometric sequences are going to have either an increasing, that's true. They can decrease, right? Yeah, they can decrease. Increasing or decreasing rate of change. Because you can have exponential growth. You can also have exponential decay. So you could see either one for this. Okay. And what you're going to see is like with exponential functions, if we do like that second difference and third difference and fourth difference like we were doing with cubics, we're not going to see it ever become constant. Like for example here, this would be 4, this would be 12, this would be, somebody did 54 minus 18 real quick. 36. Okay. And then if I try that again, I've got 4 to 12 is 8, and 12 to 36 is going to be 24. And that's like just never going to end up constant. If I had that going on out, we would see it constantly. It's increasing at an increasing rate there the whole time. So, whereas if it's cubic or quadratic, you will see that eventually become a constant rate of change. That will not happen with exponentials. All right, so let's look at an example here. So again, we can only plug in whole numbers. If I plug in 0 right here, I've got 80 times 1/2 to the 0. What is 1/2 to the 0? Should have the 80. Not 0. Doesn't say the same either. 1. It is 1. Anything to the 0 power is 1. Have you guys ever like known why that is. I'll show you something here in a second. But right now that'll be 80. All right. Now if I plug in 1, I've got 80 times 1/2 to the first power, right? This is 80 to the 80 times 1/2. What is 1/2 times 80? 40. It's just half of 80, right? And then if I do 80 times 1/2 squared here. 1/2 squared, what is it? It is 1/4. Very good. You square the top, square the bottom. What is 1/4 of 80? 20. Now we should be starting to see a pattern here, right? So that we don't have to actually do that with the fractions for the rest of this. What are we doing to our numbers each time? Dividing by half. So what's the next one going to be? 10, and then 5, and then 2.5. And that would just continue getting smaller and smaller and smaller, right? So if we graph those, we've got 80 to the 0 power. We've got 40, 0, 80, 140, 220, 3, 10, 4, 5, and then 5, 2.5. And again, I'm wanting to connect those, but we don't because this is a sequence here. If we did connect it, you know, it looks like a exponential graph there. Now, let me just show you something about why anything to the 0 power is 1. Think about what we were doing here. I had my, let's just look at the 1/2 part. Or, well, let me just use easier numbers, right? If I'm doing if I'm doing 2 to the n power, right? If I plug in 4, I would have 2 to the 4th power, which would be 2 times 2 times 2 times 2, make it 16, right? This is a side note on why anything to the 0 power is 1. All right, so if I plug in 3, right, I have 2 to the 3rd, and that would give me 8. And I plug in 2, that would give me 2 squared, and I would have 4. And if I plug in 1, I'd have 2 to the 1st, and that would just give me 2. Right? We're good here. We know how to do that easily, right? But then I get to the point where I've got to plug in 0, and I've got 2 to the 0, and I got to figure out what in the world that is. Right? But if you look at the pattern that's happening every time, what are you doing? You're dividing by 2, right? So the next natural step is to do 2 divided by 2, which would give you 1. And no matter what number we used in place of that 2, we're going to see the same thing happening, right? Every time you got that pattern where you're dividing, and then you have to divide that number by itself, and you will get 1 for that. So that is sort of an explanation of why anything to the 0 power is 1, because it sounds kind of crazy. You expect it to be 0, or maybe just itself, but you don't really expect it to be 1, but it is. There. Okay, let's keep going. Here. All right, common ratio for this sequence. Ooh, what is the common ratio for that sequence? We got 100, 102, 104.04, 106.1208. 2.04. It would be the amount added here, but it wasn't here. It was only went up by 2 here. So first of all, like if we think about how much this is increasing by, I'm going up by 2, and then I go up by 2.04, and then I go up by, I have that in right. I may have that number wrong right there. Hold on just a second. Let me make sure I got that number wrong. Right. No, that's right. Okay, and then we go, like if we subtract those, we go up, oh good gracious, that's not right, 106.1208 minus 104.04. We go up by 2.0808. So what I should see here is this is not linear, right? We're not going up by the same amount each time. So given that I'm only asking you to do arithmetic and geometric sequences, you should be thinking, well, there's got to be a number, like where I can do 100 times the number and it gives me 102, right? And then I can take 102 times that number and I get 104.4, right? How could we find that number? We're going to divide. So we take any term, it doesn't matter which one it is, and divide it by the term that's before it. So if I do 102 divided by 100, because that's the easiest one to do, I will get 1.02. Let's check to see if it works. If I do 100 times 1.02, I get this. Then I multiply by 1.02, and I get 104.04. And then I multiply by 1.02 again, and I get 106.1208. So the common ratio, which we use an R for most of the time, would be 1.02. That might seem like a weird one, but this is actually something that gets used a lot because this is like interest rates. Like if you put your money in the bank, $100 in the bank at 2% interest and it's compounded annually, at the end of the first year you'd have $102, then 104.04, and then 106.1208. The more money you have in the bank, it grows a little bit faster each time, right, for that. Okay, now what about if we want to write an equation for this sequence shown above? And we're kind of running out of time, so I'm going to kind of look at this. What is happening each time? What are we doing? We're multiplying by 3. So that's times 3 times 3 times 3 is what's happening, right? We're not adding 3, we're multiplying by 3. So when we see this, I could spend a little more time having you guys think about it, but it's going to be exponential. What number did we start with? 2. All right, so I started with 2, and I multiplied it by 3. And what's happening is with each step, you're multiplying it by 3 another time, right? So it's going to be 3 to the n power, right? So a sub n would be 2 times 3 to the n power. If you think about how this works, like if I want to do a sub 2, I'd have 2 times 3 squared, which means I would take 2 and I'd multiply it by 3, and I'd multiply it by 3 again. That's exactly what I do to get 18, right? I take 2, which is what I'm starting with, I multiply it by 3 to get 6, and I multiply it by 3 again to get 18. That second term, which this would be like a sub 0, a sub 1, a sub 2 here, would be 18. Right. There is a shortcut for this one as well. So let me get back to the main screen so I can move this box. And your shortcut for this, and oh wait, no, not that one. That's the next shortcut. Here's this one. It's going to be G sub n. They're using G's instead of A's. Sometimes I think they just use A's. I think A's are more common, but he used G's on all of his stuff, so I just did that as well, just to designate it's geometric instead of arithmetic, but they won't always do that. Sometimes they'll use A's. And they could use any letter in the world. They could use a R, could use a Z, but A is what you see most often. So G sub n is just going to be the initial term, whatever the first term is here, times the common ratio to the n power for that. Okay, here. All right, let's look at this next one. Again, we're kind of running out of time, so I'm going to do this one with you instead of letting you work on it, which I would have done if we were not running out of time. So, for this problem, fifth term, I'm going to call it G sub 5, or you could call it A sub 5, whatever letter you want to use, but he uses G's a lot here, is going to be 12. G sub 4, and fourth term is 6. Now be careful. This problem gave those to you backwards, right? Really, we should think of it this way. A sub 4 is 6. A sub 5 is 12. Put those things in order, right? What are you doing to get from 6 to 12? We're multiplying by 2, right? So if I need the 10th term, I can just do brute force method. If I want A to the 6th, it would be 24. A sub 7 would be 48. A sub 8 would be 96. A sub 9, I'm going to start needing my calculator over here, 192. And then A sub 10, what do you guys get? 384. Okay, so again, if they give you this problem, that's probably the way I would do it. But if they give you something way bigger, it might become really difficult to do this way. So the shortcut that you can use for this, that we could have used, is G sub n equals G sub k times r to the n minus k. So let's look at what we would do for this problem if we use that. If I'm looking for G sub n, I could use G sub 5 or G sub 4. Let's use G sub 5 because it was listed first. I could do G sub 5 times my common difference is 2 here to the n minus 5, which would be, G sub n would be 12 times 2 to the n minus 5. So then if I wanted to find G sub 10, I could do 12 times 2 to the 10 minus 5, which would be 12 times 2 to the 5th. And I could type that into my calculator, and I should get 384. Let's check to make sure that I actually do. Here, on the calculator. 12 times 2 to the 5th, and yes, I get 384 for that. Okay. All right, so I try to put some multiple choice questions here at the end because this is sort of the stuff that was similar to what I've seen on AP Classroom. Consecutive terms of a sequence have the values 10, negative 5, 5 halves, and negative 5 fourths. Of the following, which describes the sequence? Now, all of these say geometric sequence. They have different common ratios, or there's this option that it's not either because the common ratio of a geometric sequence must be positive. I'm going to tell you for the sake of time, D is false. The common ratio does not have to be positive. So it's not going to be D here. That is a false statement. What would our common ratio be? It is that negative 1/2. B would be our answer because I'm doing 10 times negative 1/2. It would not be negative 2 because if it was negative 2, you're multiplying every time, right? So it'd be 10 times negative 2. A lot of times people are inclined to choose A because you're dividing by negative 2 each time, but the common ratio is the number you're multiplying by each time. So if it's division, you need to do 1 over that number to get that negative 1/2. Okay? What about 18? It says consecutive terms are given 8, 5, 2, negative 1. Which could be the correct answer for that? Okay, A, arithmetic sequence, common difference of negative 3. Do you guys agree? That is correct. This is almost a vocabulary question because you should recognize that you're subtracting 3 each time, so it has to be arithmetic, right? So that rules out B and D. And then C just has to be false every time because arithmetic sequences do not have common ratios. That would be false no matter what number was with it. Same thing for B. B is false no matter what the situation because geometric sequences do not have common differences, right? Geometric is always the ratio. Arithmetic is always the common difference for that. So very good on those. All right, this one right here. I saw this one. I was like, oh, I'm not sure about what to do here. This seems complicated. It is really so easy. they are given, the general term of a sequence is given by a sub n. When they say general term, they're talking about the a sub n formula, right? Where a sub 0 is the initial value, which gives the the general term of the sequence. So it's asking what's another way I could write this. So I was trying to like think about how to do this logically. Here's what you got to do. Just distribute that 2. You've got 25 plus 2n minus 10. Then you can combine your like terms. The 25 and the negative 10. 15 plus 2n is your answer. Now that does mean 15 is your initial term, 2 is your common difference there. But you don't even really have to think about it like that. Real quick, this next one right here, I don't like when they do this. And we'll stop on this one. This one, is this the last one or is there one more after this? Last one. Okay, so real quick on this. I am going to be a little more specific because I do not like whenever they do this. If they write first term, okay, that is a sub 1. Initial term is a sub 0, which is like that y-intercept of your graph. So, if they give you something like this, the first term is a sub 1. They're telling you a sub 1 equals 6. First term sounds too much like initial term. I don't like it when they do this. I wish they'd call it a sub 1 for you. If I give it to you on a quiz or a test, I'm going to call it a sub 1 for first term because it sounds so much like initial term. But if they give you a sub 1, it is 6. Common difference is 3. So if my common difference is 3, that means I'm multiplying by 3, right? What would a sub 0 be? It is 2, because to go backwards, I divide by 3, right? So if I want to write this equation, a sub n would be the initial, which is 2, times 3 to the n power. So if it asks me for the 7th term of the sequence, oh, good gracious, no. What am I doing wrong? It's arithmetic. It is not geometric. Oh, okay. Back up. It is still 2. No, it's not 2. What's my a sub 0? It's 3 because I'm subtracting 3, not dividing because I read it incorrectly. That. Yeah. Well, I mean, I do what I'm doing now. You can mark out what we had done. Yeah. So arithmetic, you're adding 3, not multiplying by 3. So your formula is going to be a sub n equals 3 plus 3 times n, because it's linear, because it's arithmetic. I was doing geometric for that. It's how you would do it if it said geometric and common ratio. And if I want a sub 7, I'm doing 3 plus 3 times 7, and I would have got the answer choice that was there, and I would have done it terribly. And I'll get 20. Oh, gosh. Yeah, it's not. It's a bad question. 24 is the correct answer. I did not put correct answer choices there. So, real quick, your assignment is going to be this worksheet. It's just one page.